Jnanam paramam dheyam. Knowledge is supreme.
Friends, it is a good time to summarize what we have learnt in the last couple of lectures. So, we are looking at the fluid solid heterogeneous non-catalytic heterogeneous reactions, and then we identified two possible cases, two possible modes. One is a situation where the particle which is actually participating in the reaction, it does not shrink with as the reaction progresses, and then another situation where the particle which participates in the reaction actually shrinks in size as the reaction progresses. And then we looked at two possible models, progressive conversion model and the shrinking core model, and it was observed that the shrinking core model is more common in most of these situations, and so we developed a model for the shrinking core model for both the particle size, unchanging particle size, and also for those particles which were shrinking in size. And that for situations where if the overall reaction, overall conversion is actually controlled by different rate controlling steps. For example, the diffusion of gas phase from the bulk through the gas film to the surface of the core, or the diffusion of the species through the ash layer, or it is the reaction controlling. So, the expressions that we get for the time that is taken for the unreacted core to reach a certain size, which is directly correlated with the conversion of the solid species, can be summarized as below. So, for spherical particles, so it can be summarized in this table here. So, for spherical particles, suppose we take the constant size and varying or changing size. There are two possible modes. Here, changing size refers to the special case of no ash layer present. As noted in the earlier lecture, the size can change even if the ash layer is present if the densities of solid product and the reactant are different. Now, suppose if it is gas film diffusion control, if the overall reaction is controlled by the film diffusion control, then we found that T by tau, where T is the time taken for the unreacted core to reach a certain radius because of the heterogeneous reaction, that should be equal to the conversion of the solid itself, which is directly related to the amount of solid that is reacted. And then in changing size, the same the expression for the same would be T by tau is 1 by 1 minus xp to the power of 2 by 3. Here tau is the time taken for the complete conversion, that is all of the solids which is present in the core has gone for complete reaction. Now, next possibility is ash layer control, ash layer diffusion control. So, if ash layer diffusion is actually controlling the overall conversion, in that case T by tau is given by 1 minus 3 into 1 minus xp to the power of 2 by 3 plus 2 into 1 minus xp. So, that is the expression for T by tau, and of course, in changing size the ash layer does not exist, and therefore, it does not offer any resistance to the overall conversion. Then the third case is where the reaction is controlling the overall conversion. If it's the reaction control, then T by tau is given by 1 minus xb to the power of 1 by 3, and here T by tau is given by 1 minus xb to the power of 1 by 3. In both cases, the time taken for the unreacted core to reach a certain radius depends on the conversion in exactly the same way, because the presence or absence of the film or the ash layer does not contribute to the overall conversion if it is in the reaction controlled regime. Now, all this we looked for spherical particles. What happens here? What happens if it's other geometries? For example, if there is plating of metals, then normally it's not plated on a spherical particle, it's plated on other kinds of geometries. It could be a cylindrical geometry, or it could be a flat plate geometry, or it could be any other curvature. So let us look at two specific other geometries which are fairly common. One is the flat plate. Suppose if it's a flat plate, and where the solid is now present in the flat plate, and there is a fluid which is now coming on to the surface of the flat plate, and the heterogeneous reaction is occurring at the surface of the flat plate. So, in that case, if we consider the constant particle size, if we consider the case of constant particle size, then if the for a flat plate one can actually define conversion as 1 minus 1 by L, where L is essentially the half thickness. L is the half thickness of the plate that is actually being used for used as a solid reactant. And if it is a film diffusion controlling, if it's a film diffusion controlling regime, in that case T by tau is given by xp, where tau is given by tau is the time taken for the total conversion, that is for all the solids to undergo reaction. That will be given by density of the particle divided into the half thickness length scale into divided by mass transport coefficient into concentration of the species in the gas phase. If it is ash layer diffusion control, then T by tau is essentially given by xp square, where tau is given by rho b L square divided by 2 diffusivity into concentration of the species in the gas phase. And if it is reaction controlled, then T by tau is simply given by xb, and tau is given by rho b L divided by k double prime, which is the intrinsic rate constant multiplied by CAG. Intrinsic k double prime is the intrinsic specific rate, and CAG is the corresponding gas phase concentration. Now, similar expressions have been obtained for cylinder geometry, and they are as follows in this table. So, for a cylindrical geometry, the xp conversion of the solid is defined as 1 minus r by r naught the whole square. Now, here r naught is the initial radius of the core, r naught is the initial radius, of the cylinder, and r is the instantaneous radius. Of the cylinder. So, with this definition, if it's gas phase diffusion control, gas film diffusion control, then T by tau is essentially given as xb, and tau is equal to rho b into r naught, which is the initial radius, divided by 2 times kg into CAG. So, that is the time taken by the core for complete conversion. And if it is ash layer diffusion control, then T by tau is given by xp plus 1 minus xb multiplied by the natural logarithm of 1 minus xp, where tau is the time for total conversion, that is given by rho b into r naught square divided by 4 dE into CAG. So, that is the concentration of the species at the gas phase. And if it is reaction controlled, then T by tau is essentially given by 1 minus xb to the power of half, tau is equal to rho b into r naught divided by k double prime, that is the specific reaction rate, multiplied by CAG. So, this sort of summarizes the various time taken for the core to reach a certain radius if the overall reaction is controlled by different resistances which is actually available in the system. So, all these are for basically constant size system, and similar expressions can actually be worked out for varying size as well. We so far looked at the cases where the overall reaction is actually controlled by the resistance of one of these three resistances which are available, that is either the diffusion through the gas film or the diffusion through the ash layer in the case of constant particle size, or if it is a reaction controlled. So, in reality this is not the situation. In reality what happens is that all three resistances actually contribute. So, as reaction proceeds, and in fact that is true, because as reaction proceeds, even in the constant size case, what is observed is that the of course, the unreacted core radius is going to decrease. Unreacted core radius decreases as the reaction proceeds, and therefore, as a result the relative importance of various resistances is going to change. So, that is very important, because there are three resistances. As the size of the unreacted core changes, then the relative importance of these different resistances towards their effect on the overall conversion also is going to change. So, which means that no one resistance controls overall conversion all times. All time t. So, therefore, it is important to consider simultaneous action of all the resistances. So, it is important to consider simultaneous action of all three resistances. So, if you want to incorporate all three resistances, then the model for the radius of the unreacted core as a function of time, that the differential equation which basically tells what is the rate of change, relates the rate of change of the radius of unreacted core with respect to time to all the other properties and concentrations of the system, can actually be rewritten by using a combination of all the resistances, and the rewritten model will be dr by dt, that will be equal to minus CAG divided by rho b. CAG is the gas phase concentration, rho b is the density of the solid that is used, divided by r square by r naught square into kg plus r naught minus r divided by the diffusivity into r by r naught plus 1 by k double prime. That is the specific reaction rate. Now, here it is assumed that the volume fraction of the solid in the unreacted core is approximately equal to 1, and so there are three terms here which correspond to three different resistances. So, the first one here, this corresponds to the gas film, resistance, and this corresponds to the ash layer. This corresponds to the diffusion in ash layer, and the last term corresponds to the reaction resistance due to the heterogeneous reaction that is occurring in on the surface of the unreacted core. So, now suppose this is for a constant size system. So, if the particle size does not change, this is for the constant size system. Suppose if we The same thing can be written for a shrinking core, shrinking size type of particles, where there is no ash layer. So, if there is no ash layer, then the resistance due to ash layer does not exist. So, simply we can obtain the expression by removing the resistance due to the ash layer, which is present in this expression here. So, for shrinking particles, there is no ash layer. So, therefore, we can write this expression as dr by dt is minus Cag by rho b divided by 1 by kg plus 1 by k double prime, where k double prime is the specific rate and kg is the corresponding mass transport coefficient. So, now let us take an example problem and see how we can predict the dissolution of a particle of a certain type, which is undergoing such kind of a fluid solid non-catalytic heterogeneous reaction. An excellent example of that is the drugs which are actually being administered. So, the solid drugs which are administered for curing a certain disease, when they go into the body, they have to dissolve, and it is important to understand how much time does it take for the drug which is a solid particle to dissolve, and that the dosage of the drug actually strongly depends on the time taken for complete dissolution. So, therefore, it is important to model this from the pharmacokinetic standpoint of view. So, let us look at this problem. So, dissolution of solid particles. Suppose if we assume that there are all these drugs which are given inside, they are all monodispersed particles. That is, all the particles that are actually in the drug are of same size. This is not true always, but let us assume to start with that all particles are actually same size, that is, it is a monodispersed system. And then, so we need to, the objective is to find out what is the dissolution time, which actually plays an important role in the pharmacokinetics. Now, suppose if there is a species A, which is basically in the fluid stream, that reacts with certain solid, which is essentially the drug particle, and that leads to formation of products. Now, if we assume that the fluid A actually reacts with the core which contains this solid material, and if you assume that it is first order with respect to the fluid, the reaction rate is first order with respect to fluid and 0 order with respect to the solids which is present, then the question is what is the dissolution time. So, we need to estimate the objective of the problem is to find the dissolution time, the time that is taken for dissolution of these particles. So, now we can observe, we can actually observe that the rate of mass transport, the rate of mass transfer to the surface is actually equal to the rate of surface reaction. Why is this? Because the particles are expected to, as the property of the drugs are always such that the particles are expected to dissolve, and so the particles are this is actually a process where the particles are actually shrinking in size. So, there is no ash layer which is actually present. So, therefore, the rate of mass transfer to the surface should be equal to the rate at which it is being consumed for the surface reaction. So, therefore, we can write that WAR, if that is the flux at which the species is actually traveling from the bulk gas phase to the surface of the solid, that is equal to kg into Ca minus Cas, where Ca is the bulk concentration and Ca is the surface concentration, and that should be equal to the reaction rate Ra double prime, and that is equal to, if Kr is the specific reaction constant, multiplied by Cas. So, that is the surface concentration, and this is the net reaction rate. So, this is the reaction rate and this is the mass transport. This corresponds to the mass transport. So, from here we can actually eliminate CAS. So, note that CAS is a quantity which cannot be actually measured experimentally, but CA is the bulk concentration and that can actually be measured. So, we need to eliminate CAS, which is not a measurable property, measurable quantity. So, Kg into Ca divided by Kg plus Kr. So, plugging in this back into the expression for WAR, we find that double prime, that is equal to Kr into Kg Ca divided by Kr, and that is equal to Ca by 1 by Kg plus 1 by Kr. So, therefore, if we know the mass transport coefficient and the reaction in specific reaction constant reaction rate, then we will be able to actually calculate the required quantities such as the dissolution time. So, therefore, now there is a need to find out what is this mass transport coefficient. So, we can use correlations in order to find the mass transport coefficient Kg. So, suppose if we assume that the particles are small. So, under small dp, and if there is no shear stress at the, so if there is no shear stress at the boundary of the fluid and the solid, then we can actually using the Frost-Ling correlation, we can find out that from Frost-Ling correlation, we can find out that Sherwood number, which is equal to the mass transport coefficient into diameter of the particle divided by the corresponding diffusivity, that is approximately equal to 2. So, from here we can find out that the mass transport coefficient is given by 2 times diffusivity divided by the corresponding particle diameter of the particle which is actually being dissolved. So, plugging in back into the expression for flux, we find that WAR equal to Kr into Ca 1 plus Kr by Kg, and that is equal to Kr into Ca divided by 1 plus Kr into dP divided by 2 times dE, and with this can be rewritten as Kr into Ca divided by 1 plus dP by d star. So, where d star is nothing but the ratio of 2 times dE into Kr. So, that is what is d star. So, d star, the meaning of d star is that it basically tells you the diameter at which the mass transport and the reaction rates are actually equal. So, if we look at what is the expression for d star is 2 times dE divided by Kr, and that is essentially the diameter at which the mass transport rate and the reaction rate are equal. Reaction rates are equal. So, therefore, if the diameter of the particle, if this is larger than d star, then it can be expected that it is mass transport controlling, while if the particle diameter is less than d star, then it is actually expected to be a reaction controlling scheme. The overall conversion is expected to be reaction controlling. So, now in order to find the radius of the particle as a function of time, we can now write a mole balance on the solid particle, and the mole balance goes as here. Mole balance on solid particle. So, where whatever rate at which things are coming inside minus whatever rate at which the particles are leaving out plus generation should be equal to accumulation. That is the balance. Now, nothing is coming inside because it is the solid which is actually participating. So, there is no flow. So, nothing is coming inside and nothing is actually leaving, but some of it is actually being reacted. So, that is accounted in the generation term. So, if RBS is the rate at which the solid is being consumed at the surface of the particle multiplied by pi into dP square, that is the surface area of the solid particle, and that should be equal to d by dt into density into volume of the spherical particle. So, suppose if we assume equimolar counter diffusion, then the minus R A S double prime, that is the rate at which the species A is actually being consumed because of the heterogeneous reaction, that should be equal to minus R B S, the rate at which the solid is being consumed. This is because of the equimolar counter diffusion and the stoichiometry which is associated with the particular reaction. So, now this equation can further be simplified as rho into 3 pi by 6 into dp square into, that is equal to R A S into pi into dp square. So, this can be simplified as d by dt of dp, that is equal to minus 2 minus R A S double prime divided by rho. So, that is the expression for the rate of change of the diameter of the drug particle as a function of time, and how is it related to the surface reaction rate and the density of the particle. So, now this can actually be, we know what is the rate. So, that can be rewritten as minus 2 into K R into C A divided by rho into 1 by 1 plus d p by d star, and this can be rewritten as minus alpha divided by 1 plus d p by d star. So, that is the expression for rate of change of the diameter of the particle as a function of time. So, if we assume that this whole thing is a constant like alpha, so we can rewrite this expression as d by dt of dt equal to minus alpha by 1 plus dp by d star, where alpha captures the rate of the reaction divided by the density of the corresponding particle. So, now we can integrate this with the following initial condition, that at time t equal to 0, the initial size of the particle was dpo, and based on this initial condition the equation can be integrated, and integrated expression would be dpo minus dp plus 1 by d star 1 by 2 d star into dpo square minus dp square, that should be equal to alpha t. So, this provides a relationship between the properties of the system and the diameter of the particle and time. Now, in order to obtain a complete conversion for this problem, for achieving complete conversion, that is for complete dissolution of the drug. So, for complete dissolution of the drug, the dp should be equal to 0, that is all the particles are actually completely consumed, and so and the time tau, which is the time taken for complete conversion, is given by 1 by alpha into dpo plus dpo by 2 d star square. So, that is the relationship between the time taken for complete conversion and the diameter of the particle and other properties of the system. So, now this is the expression, this is for monodispersed particles, but normally the drugs which are actually administered, they are all polydispersed, that is particles are actually of different sizes. There is a population of particles, and each of these particles can actually be of different sizes, and all of them are actually simultaneously undergoing dissolution, leading to the shrinking of the particles. Now, the only issue here is that different particles will actually do different things because the size is different. Although the reaction is same, their dissolution rates are expected to be different because their sizes are completely different.